We will start now the second part of the lecture on radiation physics, and this part will be mostly focusing on charged particles, on ions. So, where are the charged particles coming from? They are either coming from decay of alpha particles that are, of course, low energy, or on the other hand, very high energy. You find them in cosmic rays. You have everything there from protons to uranium, the whole periodic table in terms of nuclei. Or, of course, you can do them at particle accelerators. You can produce charged particles and accelerate them at particle accelerators, either for research purpose or for industrial or medical applications. The interaction process, again, you have a given ion. Here, for example, is given a carbon ion with a certain energy and given fluence, a flux number of ions. Then you have an exit through a given target. The energy loss will be the difference of this. The number of incident, the number of ions out and in, if delta X is small enough, of course, so if we go to Dx, this is approximately the same. You don't have loss. We will see that you can have loss. And the energy loss is generally described with this formula, the minus d over the x, or even more commonly dividing by rho, so that this is a rho dx. It's a mass thickness. This is the stopping power. In physics, generally is expressed in MeV per grams per square centimeter, but in radiation biology, radiation therapy, this is generally called LET, linear energy transfer, because it's the energy per unit track. And the most common unit used is kV per micron. Of course, in water. So you assume that the density is 1 gram per cubic centimeter. And then you have and then you use the unit of kilo electron volt per micron of water or for micron of tissue. Now, which kind of interactions you have between charged particles now and matter? Well, again, you have, of course, you have elastic scattering with the nucleus, the Rutherford experiment, if you remember. The inelastic scattering with the electrons, so this is the electronic stopping, and we will see that this is the main path of energy loss. And then you can have nuclear reactions, like fragmentation if you have a heavy ion. You can have Bremsstrahlung, but we saw already that Bremsstrahlung is very insignificant, and also the production of Cherenkov light can be very spectacular, but is not important in terms of energy loss. So we will mostly focus on the inelastic scattering here. And inelastic scattering is described by the so-called Bethe block formula. The first approach is the so-called Bohr, was actually proposed by Bohr. And the formula is apparently complicated, but it's not so complicated. The derivation of the formula is given, I will not do it during this lecture, it's given in a separate file that is uploaded on Moodle, so you can look at it if you want. It's very useful, I think, to look at it. Essentially, you see, it's based essentially on the Coulomb interaction between one ion that is moving and this almost remains unaffected by the Coulomb interaction with the electrons. So if you solve the equation, you come with the formula like this one, where it looks complicated, but you will see it's not so complicated. This is the Avogadro number. This is the effective charge, and we will see the meaning. This is a little bit unexpected. Maybe it's called effective charge of the projectile, so the ion that is losing the energy. Beta is the velocity of the ion. This is a constant, of course, and this instead the rho Na Z divided by A. These are the properties of the target. Essentially, is the number of atoms per the number of electrons per unit volume in the target. And these terms, this logarithmic term takes into account the relativistic effect. The I is important though, is the ionization potential. So it's essentially is what is the ionization potential for the target. So it's a property of the target. Now, what is the effective formula? Well, the effective charge. Before I introduce the effective charge, I want to show you one thing. If you look at the dependence on the velocity in the Bohr formula, you see that when beta goes to zero, this energy loss will go to infinite. So it makes sense, of course, is the usual story like for the cross section. When you increase the velocity, your energy loss decrease. You have less interaction with the electrons, so you have less energy loss per unit track. So when you reduce the velocity, when you are slow, you will have more interaction with the electrons, and then it's more likely that you ionize the matter, and then you will lose more energy per unit track. But it's impossible that going to zero, this becomes infinite. Doesn't make sense. Eventually, you lose all the energy and you stop. So you have no more energy. At that point, this has to go to zero, not to infinite. To take into account this effect, the charge is changing. But this is true. I mean, when the ion slows down, it starts to capture electrons, and eventually the charge goes to zero. And goes to zero faster than the velocity. In fact, you see it's an exponential formula derived by Barkas. You see here the nice example of the effective charge as a function of the energy for different ions. You see helium, carbon, neon, argon, krypton, and uranium. And you see that when you go to very high energy, the ion is stripped, you see, and the charge is what is supposed to be. For helium is 2, for carbon is 6, for neon is 10, and so on and so forth. But when you go to low energy, you see that the ions start to capture electrons, and then the effective charge decreases. Of course, for the single ion, the decrease is not a continuous function, it's stepwise. You know, for helium, of course, either the charge is 2, or is 1, or is 0. But on the average, if you take a beam with the 10 to the 9 helium ions, this will be the general trend of the effective charge of in the average beam. Now, the Bohr formula has been reformulated many times. This is this is still the Bohr formula. Let's say the classical approach with the Bohr formula is only written in a slightly different way that shows you the dependence on the velocity, the dependence on the target, and the logarithmic term. Now, with the more refined description by Bethe in 1930, using quantum mechanics for the description, Bethe came out with this formula, which is, if you see, is exactly the same as the Bohr formula, except for the logarithmic term that now takes into account quantum effects. And you see, but you see that the dependence on the projectile terms is still here. Square of the charge divided by square of the velocity. So you go up with the charge, and you go down when you increase the velocity. This is the target dependent. So of course, you can divide rho here, but if you see the target dependence, apart from the density, of course, it depends on the density, but you can, if you put rho here, there is no difference. You define energy loss per gram per square centimeter. This term here is not so different for the targets, because, you know, for light elements, the ratio charge to mass is almost always 1/2, except, of course, for hydrogen targets. In a hydrogen target, this is 1, so it's much higher. And this is important, we will see in radiation protection in space. So if you use hydrogen, you lose more energy. But then when you go up, you take very heavy elements, then the ratio becomes smaller than 1/2, because of course you have an excess of neutrons. The ionization potential is approximately in water 13.5. I mean, it's 13.5 for the charge of the target. This is a formula to calculate the ionization potential that is here in the logarithmic there. Now, this is how it looks like if you plot in a log-log scale the LET now in kV per micron. This is in water as a like, and you see that this is protons, helium, carbon, and then you go to heavy ions. Up here there is uranium. So the behavior is always the same. You see, you have at low energy, you have an increase until you reach a maximum. So keep in mind that this increase at low energy is due to the Barkas effect, so that eventually this must go, the LET must go to 0 when the energy goes to 0. So then you reach a maximum, and then you go down essentially as 1 over beta square. Of course, when you change the charge of the ion, the LET increase goes with the square of the charge. Typical example, you know, to give you some typical numbers. If you take a slow and heavy ion, you see this is a low energy, 4 MeV, similar to the energy of an alpha particle, but very heavy ion, uranium, the LET is very high, 15,000 kV per micron. Slow and light, 4 MeV, but now is a carbon, 330 kV per micron, of course, because the charge is different. Same charge, but higher energy, lower LET. And here you have a proton, fast. This is what is used in proton therapy, for example, very low LET. We will see that so far I told you that the dose is the most important physical parameter to characterize the biological response, but the LET is the second one. So the reason why, the main reason why different radiations, I told you, have different biological effects at the same dose is that they have different LET. And the difference in LET reflects a different biological effectiveness. These are visual examples, you see, of the tracks of different ions in nuclear emulsions, where you see it's like a picture of and you see that increasing the LET, what is the difference when you increase the LET? In this case, you see you have light ions, these alpha particles, and then you go up. Now, to be precise, let's say this is again a similar plot, but extended in energy. You see, this is the low energy part, the peak, the beta block region, 1 over the square of the velocity here. And then you have the relativistic, quantum relativistic region. You see, you reach essentially, for the usual reason of time dilatation, you reach a minimum of ionization, but then the time, if you want, increase, and then you have a relativistic rise, not so strong, you see, and it's not going up always, because for a quantum mechanical effect, this is also saturating, it's called the Fermi plateau. This is at very high energy. You see, this is in the order of 10 to the 6 MeV per nucleon, so it's 10 to the 12 eV per nucleon. On the other side, you see, when you have the maximum is here, because you start to have electron capture, so you enter in the Barkas region. The more electron capture you have, the more the energy loss is decreased, and at the end there is a further, let's say, quicker decrease, not due to the electron capture, but to the interaction with the nuclear potential. So now, when the ion is sufficiently slow, you start to have nuclear interaction, and so you lose more energy quickly at the end because of the nuclear interaction. So you see, the nucleus-nucleus energy loss is actually only visible when the ion is only stopping. So all this beta block region is dominated by the energy loss of ions for ionization of electrons. So what is the take-home message, if you want? Please look at the demonstration of the Bethe-Bloch formula if you want, but the take-home message is that the Bethe-Bloch formula works, okay, does not really work for the electrons, because in reality it's similar for the electrons, but the assumption in the Bethe-Bloch formula is that the ion is not deflected by the interaction with the electron. So for electrons, you have to do different assumptions because it's they have same mass. Small energy, the charge, effective charge decrease, and then you have a peak at the end. For large energies, essentially it goes like the square of the velocity, so goes with the energy, with the kinetic energy, is inversely proportional to the kinetic energy. And the LET is very important in radiation biology. There is a slightly different concept, which is called restricted LET. Restricted LET is useful if you want to take not all the energy. It's a little bit like the story of the Kerma and of the dose. Here, the LET is all the energy loss per unit track. But if you want to take only the energy along the track, then you can put a cutoff to the delta rays that are coming from the track. You remember the concept of delta rays. And then you come out, which is known as restricted LET. We will come back to this concept, but this is how the formula looks like. So this is again to show you the nuclear versus electron stopping power. If you remember, the electron stopping power is here in the Bethe-Bloch region. Then you go down, you start to have capture, electronic capture here. So you have a decrease in the stopping power, and only at the very end, you start to have the loss due to nuclear stopping power. You see, nuclear stopping power is essentially only important in a region of, you see, this is 0.01 MeV, so we are talking about 10 keV, and at this point, you start to have nuclear interactions that increase the energy loss. So now, this is the curve, no? Where you have the energy loss as a function of the energy. It's interesting, this maximum here is interesting, because what happens now, you can say, okay, instead of plotting the energy loss versus energy, let's see if I can plot the energy loss of the dose versus the depth. Why is that? Because you see, essentially, when I start, so when I enter at high energy in any material, let's say that I'm here, I'm fast, okay? I'm very fast. My energy loss is relatively low, but then I start to enter, and you see the energy loss tends to increase until I am in this region, and then at this point, you see, I reach a maximum where my energy loss per unit track is extremely high. Then in this region, I deposit a lot of energy. Behind this point, I am in the so-called Bragg peak. So you see, in principle, for a single particle, there is no, we will come back to this one, this is a struggling. So for a single particle, this Bragg peak is extremely sharp. You have energy loss, and then you have a sharp peak here where you deposit your energy, and then the particles stop. This is simply reflecting the Bethe-Bloch formula, but now is the energy loss or the dose versus the depth. The length of the path before the particle stops is called range. So this is the range of the particle. And this is how they look like, the Bragg curves in water. This is measured Bragg curves, those thickness in water. Carbon ions are carbon ions, of course, these are all measurements coming from GSI. Different energy, you see 135 MeV per nucleon, 195, 270, 330. Of course, if the energy is higher, then the range will be higher because, you know, I have more energy to travel. And you see the peak seems to be lower because it's broadened more. This is the struggling. So because of the struggling, you are not so sharp, but the different particles lose different energies, a stochastic process. And so the Bragg peak is a little bit more broad than it would be for a single particle, or if you have a small path inside the matter. Now, it is still, I mean, it's clear already, and we mentioned this already last time, that if you want to do therapy, it's good to have the Bragg peak, you see, because you have almost very low energy loss here, normal tissue, and then you have the Bragg peak. But unfortunately, you see the Bragg peak is very sharp, and the tumors are very big. So normally what you do in particle therapy, you overlap different Bragg peaks at different energies to create what is known as spread out Bragg peak, you see. So if you make the sum of these Bragg peaks, you come out with something which is a spread out Bragg peak, where you have a region here of extended Bragg peak. And that's a comparison between the depth dose profiles, you see, for 18 MeV X-rays, so high energy X-rays, cobalt gamma X-rays, 1 MeV approximately, 120 kilovolt X-rays, you see how sharply decline, and what you have with particles. This is carbon at 2 different energies. This is actually protons. You see that protons are very similar to carbon, but their struggling is a little bit bigger because they scatter more. So you have a higher struggling as compared to carbon ions. So actually, how do you calculate the range? I mean, it's clear, I think, now that the Bragg peak figure is only the mirror image of the Bethe block formula plotted as Stockton power versus energy. It's simply the mirror image. And to calculate the range, you have to do the integral of d in d of 1 over d over dx. So, which is, of course, the integral of dx, and that is the range, the total range, you see, the total range of the particles. How does the range depends on the charge and the mass? This is important to compare the range of 2 different particles. So if you have particle 1 with mass m1 and charge z1, and particle 2 with the mass m2 and the charge z2, the ratio R1 divided by R2 will be the ratio of these 2 quantities. So can be written in this way. And this means, for example, that if you compare 2 isotopes like carbon-11 and carbon-12, the range is not the same. This is interesting because carbon-12 used for cancer therapy makes fragmentation, lose a neutron, so you produce some carbon-11. Carbon-11 is a beta plus emitter, so you can visualize it by PET, by positron emission tomography, but the range is not the same. You see, the range of carbon-11, based on this formula, will be smaller than the range of carbon-12. If you compare, for example, carbon-12 and boron-10, you see the range of boron-10 will be higher, 1.2. Here you also have to calculate the charge. And interestingly, if you compare carbon to protons, then the range of protons will be 3 times the range of carbon. So when you compare carbon and protons, you have to consider that there is a substantial difference in range. This is a plot, you see, showing the range as a function of the energy for different ions. You know, this is for protons, for helium, for carbon, for oxygen, and for neon. Of course, for heavier ions, they lose a lot of energy because you have high charge, and then you cannot reach these large ranges that you can get with light ions. Now, this is let's go back to the case of the struggling. You see, if you have a single ion, this single ion, according to the Bethe block formula, you know, is running, is losing little energy at the beginning, then is losing a little bit more energy, then captures and stops. However, if you consider the struggling, you see this is a real case, this Bragg peak will be extended because the different ions will have different probability of interaction and different probability of capturing the electron. I mean, so some of them will capture the electron first, others later. Some of them have more interaction with the matter, others less. So you always, like in a marathon, you know, when you have a marathon, you start all together, but very soon you see that the platoon is take like a triangular shape with someone who is running faster and someone who is running slower. So this is called struggling, and you can represent it with a Gaussian distribution essentially. So the delta E as a Gaussian distribution, which is given by formula like this one. The important part, of course, is the sigma. So to know how big is the struggling, you have to look at the sigma of this distribution, and the sigma of this distribution can be represented by this formula. You see already here that the sigma goes up, for example, with the delta X. So if you have more thickness, you will have more interaction, you will have more struggling. And these are examples. Generally speaking, the sigma, the struggling is proportional to the mass to -1/2. So this means, and you see it here, that for protons and carbon ions at the same range, you see they have different energy, of course, to have the same range, but at the same range, different energy, protons have a larger struggling than carbon ions, because of course the sigma goes like n to -1/2. Typical values, you see, typical values of the range and of the struggling are given here for different energies, like this is carbon, 90, 198, 270, 30, 30 MeV per nucleon. The range is this is in millimeter, so 1 centimeter, almost 2 centimeters here, 7.6, 13, 18. You see that typically a tumor is here, down here, so you need an energy in the order of the hundreds of MeV. And the struggling goes up. You see, you go from 0.7 millimeter here to 7 millimeter here. But still, it's too sharp, of course. So you need a ripple filter to widen the Bragg peak. You have to do a spread out Bragg peak. So you cannot use the struggling for spreading the beam. Now, the last particles that we have to talk about is neutrons. Neutrons from the physics point of view, neutrons are very well studied, especially in radiation protection, because they were in the atomic bomb, they were in nuclear power plants. Of course, neutrons represent one of the main risks for radiation protection. So they were studied in the 60s and in the 70s very intensively. There was even neutron therapy. Then they declined, the interest in neutrons declined. There is now a renewed interest in neutrons that come from high energy neutrons in particle therapy, high energy neutrons in space, and also from the risk of nuclear terrorism, as we will see. So interaction, of course, again, interaction of the neutrons can be elastic and inelastic, as for all particles. There are then, in addition, absorption reaction, a little bit like for the photoelectric effect, if you want. But now the absorption is not in the atom, but is in the nucleus. And then there is, you see, the capture, this absorption reaction are divided in capture, and gamma, for example, is an exothermic, or charged particle that can be endo or exothermic, or neutron producing that is always exothermic, and fission, of course. You can break, this we will see when we will talk about the nuclear weapons, but you know already, of course, that very heavy elements like uranium can be broken up by neutrons in what is called fission, and a lot of energy is released in this fission of the nucleus. The absorption of the neutrons, this is again always similar to the absorption of the photons. It's the same principle. So of course now you will have a different cross-section now in the absorption coefficient for neutrons. And actually the cross-sections are expressed normally in barn, where one barn is 10 to minus 24 square centimeters. Now, the cross-sections are generally additive, you see, and you have the total cross-section is divided in absorption and scattering, and the absorption cross-section is divided in capture and fission, and you can sum them up to have the total cross-section. So you see, the total cross-section will be scattering plus absorption, and absorption will be capture plus fissions. That generally is more capture, let's say, is the gamma, is the n gamma reaction, except for some elements where fission is really important. This is an example. So as usual, you see, this is now the energy in electron volt from very, very low energy, 0.01, the thermal neutrons, to very, very high energy, 10 to the 7, the fast neutrons. You see, the behavior is always the same. You have a decrease. Of course, the cross-section goes down with the energy, as all type of cross-section, but you have a fine structure, especially in this region, let's say between 10 electron volt and 1 kilo electron volt, because this is the epithermal region, and that's where you can have capture effects. So you see, this is the thermal region that essentially goes like 1 over the velocity. And the epithermal region is where you have resonance, where you can have some resonance reaction. And this is the fast neutron region, where again the cross-section goes down with the velocity, like in the thermal region. The scattering, of course, is really like a billiard scattering. Of course, the interaction here, the neutrons do not interact with the electrons, because of course neutrons are hadrons and they have no charge. Electrons are leptons and they have charge. But the neutrons interact with any other hadron, and in particular, of course, with the neutrons themselves or protons that they find in the water. Of course, in particular with the hydrogen of the water, you can have this nice scattering, you know, of the recoiling nucleus and incoming neutron. Of course, the scattering is a very easy classical physics problem, you know, and you know, it's like in the billiard, the balls is one of the first things that you study in physics. You can demonstrate that considering the angles of scattering, the energy of the scattered neutrons will be given by this formula. And the minimum energy, you see, the minimum energy is in head-on collisions. Then in this case, you have the energy is given by this formula. Now, it is important to realize that the neutron interact with protons. The protons release the energy. The event is not as common as the stopping power of charged particles, because now we are talking about nuclear interactions, not electron interactions. So the neutron flux dose rate conversion factor is given by these curves. It's not easy to derive. And you see that this is the neutron flux dose rate in these units, and this is the energy. So it's the conversion factor from millisievert per hour. The flux is in neutron per square centimeter per seconds, millisievert per hour, and this is the energy. You see that it's higher, the conversion factor is higher when you take thermal neutrons, and then when you go to fast neutrons, it drops. So the conversions, let's put it this way, the conversions in those especially for fast neutrons, is very poor because their interaction is not so common. So having a high flux of neutrons does not necessarily mean that you have a high dose. In fact, does not. The neutrons in radiobiology are characterized by these nuclear interactions, especially with the protons. So low energy protons that are now charged particles, low energy protons are relatively high LET. Because the charge of the proton is only 1, the LET is never too high, but you can have LET in the order of 20, 30 kb per micron. And they have a very high biological effectiveness. So the high LET of the protons that irradiate everywhere, because it depends on the interaction of the neutrons, give high biological effectiveness, but make no mistake, is not a biological effectiveness per unit neutron. Is a biological effectiveness per unit dose, because the fluence dose conversion factor for neutrons is low. So you need a lot of neutrons to produce a dose that with charged particles you will produce with very, very few particles. And this is now the end of the presentation. And this closes the lectures on basic radiation physics. Then we will meet next time, is next Wednesday on Zoom for a question and answer, and maybe also some exercises if possible. And then in the next lecture, instead, we will still work on ions, but we will look more to the nuclear interaction part. You see, so far we only touched the electromagnetic interaction, the Coulomb force. Next time we will see the nuclear interactions. Thank you very much.